So starting a new chapter, chapter 6, arrays. An array is a sequence of values. Previously, we pretty much have only been holding one piece of data in a variable, right? Name is equal to, Bob. Not name is equal to Bob, comma, Joe, comma, Sam, comma, Susan, comma, Lily, right? So we're only dealing with one piece of information at a time. Or age equals 30, rather than age equals 30, comma, 27, comma, 65, or score equals 60, rather than score is equal to 60, comma, 95. Well, that's the kind of stuff that you can do with arrays. An array is a sequence of data. I'm going to make some notes here to the effect that, all right, here's a note that I added before class began. The difference between a pretest and a post-test loop, which we've already covered. Just a reminder, Python doesn't have post-test loops, but a do loop is called a post-test loop because the test happens after the body. All right, so onward. Chapter 6. An array is a sequence of values. Like scores is not just one value, but scores is equal to 100, comma, 90, comma, 40, comma, 100, and something like that. Now, that's not how you define an array. It's just a loosey-goosey English explanation. In our language, we could define it with a syntax like this. In Python, colon. Same thing, except it uses square braces around it. 100, comma, 90, comma, 40, comma, 100. So that's our list. Excuse me, I keep calling it a list because that's what it is in Python. But the book would call it an array. So I need to explain the difference between a list and an array. So, important notes. The book talks about arrays, not lists. Python supports lists, which we can use as arrays. But they're more powerful than arrays. How so? Arrays have limits. Arrays are fixed in length, meaning that you can't add anything to it. You can change the values, but you can't add to it or you can't delete an element from it. So you can't append to them, and you can't delete from the middle or the front, right? Something like that. Lists are not fixed in length. So you can append or delete. I'll modify the attendance to show you here. But you can treat a list like it's an array. So the guy who invented Python just decided, hey, I'm not gonna even mess with arrays. Everything is a list. Most other languages don't do that. Java, C#, stuff like that don't do that, but Python does. But everything an array does, a list can do. A list can just do more. So for this chapter, I will use those terms interchangeably. I'll try to use the term array because that's what the book calls it. But in Python, they're lists, so sometimes I might call them lists. Just remember that list is the Python-specific version of it. And the big difference is that arrays are fixed in length. We can't add things from it to it. So let's define a couple of arrays. Here's an array of 10 integers, or 100 integers. Declare an array of 100 integers. The syntax is pretty weird looking, but it's weird looking in other languages too. Nums is equal to square brackets in square times 100, right? If it needed to be 100 strings, we'd put quotes in there instead. declaring the name. All right. That is an empty array, though. Everything is 0 in it. I guess I wouldn't call it an empty array, but all the elements are 0. We could start putting data in it now, if we wanted to. I think I'm going to just change this to, like, 4 integers, right? Because I don't want that many digits to print. So num subscript 0 is equal to a 1, 2, 3. We've changed the first element in it. Why don't we add a print statement showing what the array looked like before we started playing with it? So I stuck a print nums above that.
So you don't have to put a comma after the 1 and the 2?
This is just a piece of data. Yeah, if I was making it a list, 1, 2, 3, let me roll with this just for a second, it'll be clear. Num1 is equal to a 4. Number 2 is equal to a 5 and a 6, and a number 3 is equal to a 7, 8, 9. Okay, so we have 3 values. The first one is 124 values. First one's 123. The second one's a 4. The third value is a 56. And the next value is a 7, 8, and 9. And so the reason I didn't put commas or anything like that in there is because I wanted it to be 123. Okay. Well, now let's print it out. But then again, if I have a double quote that's wrong, then it's not going to work. A triple quote. Where did I do that wrong? Oh, I had it one way down to the bottom. All right. Delete all that blank space. All right. Num is not defined. Now, why would that be? Because that's my variable name. Right, that's my array name. And then all of a sudden, I started calling it num. Well, that's just like your name is Sam, but I'm calling you Fred. You're not going to like it. Let's fix all that. All right, and so before we started filling in the data, it was all zeros. If we wanted it all filled in with -1s, we could change that 0 to a -1. And when we printed it out, it'd say -1, -1, -1, -1. Then we changed the values. First value became 123. The last value became a 7, 8, 9. Now that's changing the values piece by piece, element by element. We may want to set them as we create it. Here's what we could have done to save ourselves some time, because this took like 5 statements. We declared it, and then piece by piece we stuck data in it, and if there were 100 elements in it, that'd be real tedious. So instead we could have done this. Nums is equal to 1, 2, 3, comma, 4, comma, 5, 6, comma, 7, 8, 9 in square brace, and then we would want to print out our variable again just to see what it looked like. Now, the second and the third thing we print are going to look exactly the same, right? This is a short way of doing it. This is called using an initializing list, or using an initializer. And this is setting the values element by element. Something to notice is that the length of our array is 4. So we can access elements 0, 1, 2, and 3. Just remember that if you're counting like a computer, the first one's always 0 rather than 1. So if you were the first one to move into the apartment complex, you'd be in apartment 0 or motel room 0 rather than 1 if we were computers. It's just called zero-based indexing, and that's why we had a homework 0 to just try to clue that, keep as a sneak preview of that feature. So a fancy techie way of saying that is to say if the length of the array is n, we can access elements or element subscripts or indexes. Those terms are identical. Subscripts, indexes 0 to n minus 1. So since the length was 4, we could go from 0 to 3. If the length is 100, we can go from 0 to 99. So let's make an array of 100 strings. I'm just going to call it SA for 100 strings. So square brace, quote, quote, end square, but there's going to be 100 of them. And so the first element is 0, and the last is 99. If you try to go to 100, it's going to crash. Anybody getting syntax errors? I don't think I have any in my code right now, so I'd like for you not to either. Yeah. You know, and if we printed out SA, it would be really long, right? Because it's got 100 elements in it. Right. 100 strings. What if we wanted something more interesting than little blanks, right? We wanted 100 smiley faces. We could put those in there. Then when we printed them out, we'd see 100 smileys. I'm gonna delete that, but we could. But I am going to put a comment to the effect of what we just did. Declare an array of 100 empty strings. That's what that did. So we've seen ourselves declare an array of 4 integers, like that, 4 numbers, and now we have an array of 100 strings. And it's about time to actually look at the PowerPoint. So an array is a series or list. I'd prefer to use the term series because a list has a very specific meaning of variables in the computer memory. And they all have the same name and the same data type. Very important that they are, right? They certainly do have the same name, right? Every number had the name nums, and they were all distinguished by their address, right? Just like if I live on Forest Lane, we all live on Forest Lane, and we're only distinguished by our addresses. I live on 224, you live on 228. Trent lives on 225 across the street, whatever. So let's add that as a comment. All the elements of the array share the same name and the same type. Now again, Python being a weird thing would let you store things of different types in an array. I'll give you an example of that and maybe I'll delete it, right? But we could declare a list that had a number as the first one, and then, a string is the next one, and then, a float for the third one, and a bool for the fourth one, and then a turtle for the fifth one, right? Python supports that because Python's kind of a weird beast. It's more flexible. So I'm not going to mention that they all have, I'm not going to mention that Python is an exception to that because I want you to basically remember that an array is a list of all the data of the same type because that's how we use it. It's just the fact that Python offers you the idea that you can stick something else in there. It's not formal. And every element has a different subscript, a different index. Each element has a different subscript, parentheses index. Same idea. If I say name subscript 1 or I say name index 1, they both mean the same thing, and then what you type is name square brace 1 in square brace. Examples. Nums subscript 0, nums subscript 1, and so on. Or nums index 0, nums index 1. So the 0, 1 is called the index or the subscript. Same things. So what can you do with lists or arrays? Well, our MP3 player, our phone, has a list of contacts and a list of songs in it. Your bookmarks, your bookmark bar has a list of favorite websites that you like to go to. You have a list of test scores. Each month you get a list from the bank of a list of checks you write. It's weird. I no longer balance my checkbook because I don't hardly ever write a check, right? So I just trust that the bank is keeping track of it correctly. Anyway, so you get a list of all the checks that you've written and a list of all the, things that were deposited. All of those things could be lists. Our examples are going to be a little bit simpler than writing something that'll do checking, right? Something like that. So each place in the array, each box in the array is called an element. When I was looking up here, that's an element. 1, 2, 3 is an element. 4 is another element. 5, 6 is another element. 7, 8, 9 is another element. So let's say that. Each place, each value is called an element. A real techie programmer term for putting values into an array is called populating an array. I guess because we just needed a special term for it. So if we wanted to make it as complex as possible, we would say the act of assigning values to an array is called populating the array. Now I'm going to word it in English instead. Putting values into the array is called populating the array. More colloquially, I'll probably say filling the array, right? So I think of populating as like populating, populating the planet or something like that. You don't say that you populated the apartment complex. You say you moved in, right? Interesting term, but I'm not a stickler about it. The size of the array is the number of elements it will hold. We had 100 strings. We had 4 numbers. The subscripts or indexes always have to be integers, right? It doesn't make sense to try to access number 1.5, right? What the heck is number 1.5? That's like the Hogwarts having a train, a train stop that was, a fractional 1. And in the real world, you don't have a fractional train. You don't have a fractional index, right? I live in apartment 27.325. That would blow the mailman's mind. So the index has to be a whole number. So the subscripts start at 0 and go to 1 less than the number of elements in the array. I've already mentioned that. Subscripts start at 0 and go to 1 less than the length of the array. Just make sure I don't have any syntax errors. We haven't written any new code, but I like satisfaction of knowing that I haven't broken my existing code by adding comments. All right, so how arrays occupy computer memory? They're just a series of spots in computer memory. In some languages, each floating point might take 4 bytes. And so this would be 4 bytes, and then the next 4 bytes would be dedicated to another floating point number, and the next 4 bytes would be dedicated to another floating point number. So they're all in a row, stored in the computer's memory. So an array is a list of data items or a series of data items in contiguous. Contiguous just means that they come one after the other, right? Blip, 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 contiguous. Each data is called an element. Each array element has the same type and it says and the same size. All right, I'll roll with it. Each element is differentiated from the others by their subscript, which is a whole number. It's kind of restating the points I made, so I'm not coming back and adding new comments yet. And the usable subscripts go from 0 to 1 less than the number of elements. And each array element can be used in the same way as a single item of the same type. What does that mean? Well, like I could just do this, x equals 3, y is equal to 4, and I could say z is equal to x plus y. Well, x and y and z could all be array references, right? Nums 3 could equal nums 2 plus nums 1. You want to add 1 to x, x plus equals 1. You want to add 1 to one of these array values, num subscript 2 plus equals 1. Right? So anywhere you have an integer, we could instead use an array element instead, because that array element is an integer. Now that's assuming it's of the right type. Right? We had a string array up there, and you couldn't add a 1 to the string array. I'm not real fond of this page, but I'll mention it. How an array can replace nested decisions. You can list employees who have claimed 0 through 5 dependents, assuming that no employee has more than 5 dependents. And so you could figure them out. Element 0, meaning that they don't have any dependents. There's 43 people in our company with no dependents. There's 35 people in our company with 1 dependent. There's 24 people with 2 dependents. There's 11 with 3 dependents, and so on. Now this makes a note that the application does not scale to more dependents. Like say, I guess we could have a really huge number of dependents. Yeah, 107. 107 dependents. Are we going to make our array 200 elements long so that we could have 107 dependents? Meh. Probably not. So we could do something like that though. We might want to create some random numbers and stick them into the array to count the number of times we rolled a 2 or 4 or 6 or an 8 or something like that. So 2 dice rolled together can create any number between 2 and 12. So let's allocate an array from 0 to 13 just to make sure that we have enough so that we could put 12 in there. And we're going to call that roles. Roles is equal to, we need space for 13 of them. Why? Because I want to just be able to say 12, right? Or I just want to be able to say 2. And yeah, we're going to have a couple of blank ones at the beginning, but that's okay. Now let's write a loop that's going to add 2 dice together over and over and over and then fill in the place in the array, incrementing it each time. Like every time I roll a 7, it's going to add 1 to the 7th element. Now to do stuff with random numbers, we have to import the random library. So import random. Maybe we'll just do 100 so that if we see it says 35, we can say it's 35%. So for n in range 100, let's get some die rolls. dr for die roll, I don't know, is equal to random dot randint 1, 6. That's one of our die rolls, but we're going to add another one to it because we're rolling 2 dice. Die roll plus equals random dot randint 1, 6. And now let's add that to our array. Rolls subscript dr in subscript plus equals 1. If we roll a 7, we're going to increment the 7th box in our array by 1. So if we rolled a 7 total, we are incrementing rolls subscript 7 by 1 to indicate that. Now we could print that out with a for loop because it's just a list. A list is an array. I'm going to print out the rolls with a statement for x in range. Now our die rolls can go from 2 to 12. So I'm going to put 2, 13 in my range to support that. So for x in range 2, 13, we're just going to print rolls subscript x. So print parentheses x, comma, rolls subscript x. And it's going to print out the number of times we rolled a 2 and the number of times we rolled a 3 all the way out to the number of times we rolled a 12. I guess a game of craps is played with 2 dice, right? And maybe you roll 7 more often than anything else, and so they've written the rules to where you lose the game of craps if you roll a 7, something like that. All right, and here we go. We rolled the dice 100 times. 21% of the time we got a 7. It's the most common one. Only 1% of the time did we get a 12. 3% of the time we got a 2. And if we ran it again, we get slightly different results, but it'd be very similar. This is called a bell curve distribution. Bell curve distribution meaning that, you know, it's shaped like a bell. If this was like a graph, the ends of it would be low, and then the middle of it would be real high, and then the end, and then the final side of it would be low again. We could draw that graph if we wanted to with a turtle or with asterisks or something like that. I think we could make our print statement a little bit clearer, like print x, comma, quote, was rolled, end quote, comma, rolls, comma, quote, percent. Something like that, just to make it clear as what we're looking at. All right, so a 2 was rolled 1% at a time, a 12 was rolled a 4% at a time, and so on. The more times we roll the dice, the more perfect the distribution would be, the more accurate, right? Just like if you roll a die, you know, 100,000 times, then you're more likely to, you know, get a perfect average going all the way through it. But then we'd have to modify this percent thing. Just for grins, I'm going to change that to 100,000. It took a while, but then we would have to divide all of our answers by 100 to get it, or, you know, by 1,000 to get it back to being 2% and 5% and stuff like that. I'm going to make that change, but then I'm going to undo it all. So don't make this change with me. There we go. Right. This is a more perfect bell curve distribution. 2s are rolled least often, about as often as 12. 3s are rolled a little more often. Why? Because there's only one way to get a 2, right? That's to roll a 1 and a 1. But there's more ways to get a 2. A 3, you could roll a 1 or a 2, or a 2 or a 1. And there's a lot more ways of getting a 7, right? You could roll a 1 or a 6, or a 6 or a 1, or a 2 and a 5, or a 5 and a 2, or a 3 and a 4, and a 4 or a 3. So that's why 7 is the most commonly rolled one. Anyways, this is what the book was talking about when they said that you can use it to handle multiple values. Then the book goes off in slightly different tangent, and I don't want to really go into that tangent. You can read that part of the chapter if you want. All right, I'm going to undo those changes. I'm going to remove that divided by 1,000 and change this back to 100 so that it really is, quote, percent. All right, good enough. I want to make sure everybody's got this working now. Let's pause. All right, I'm going to scroll up to the top in case you at home were following along and getting errors in your code. You can eyeball it. This was the first chunk of code. Stop the video if you need to. We got some more code here. And then we got to our little die roller thing. I'm going to add a comment telling us what's going on here. we are going to use an array to create what's known as a histogram. That's what we did of dice rolls. It's actually called die rolls, but I don't care. We'll call them dice. Dice rolls, rolling 2 dice 100 times to find out what values are rolled the most often. And in here, I'm going to put a comment that roll 1 dice. And then the next one's going to say roll the next and add. And then we're going to increment that position in the array. All right, just a couple comments. Using constants with arrays. You could hold the size of an array in a constant. You could store array values as a constant. You can use subscripts as a constant. Well, Python doesn't even support constants, but we could fake it by using uppercase letters to pretend that they're constants. So something you'll quite often see is, max, something like this, max underscore scores equals 20. A class only offers 20 scores in it. And then you could declare an array of test scores. Tests is equal to, and it's an array of integers, so I'm initializing them to 0, times max underscore score. Now we have an array of 20 ints that we could fill with scores. But if we felt like changing the max score variable, we could. We want to print those arrays out, we could. For I in range underscore or subs for I in range parentheses max underscore score in parentheses colon print I comma tests subscript I. And we don't have many tests in here, right? Let's put at least one value in there. So test subscript 97, right, is equal to 100. Somebody took, wait, it can't be 97. What's the highest value this array can hold? What's the highest element? Since it's 20, it can be 19. And there we go. Element number 19 to 100, because that's what we assigned it is. How about test score number 1? Or the first element is 0. So test subscript 0 is equal to 5. They didn't do good at the beginning of the class, and they got better and better as they went along. Okay, so there's a 5, and there's 100. So here's an example of using a constant. To hold the length of the array. Now in this language, you can get the length of the array just with the len command, which is what I should have done here rather than hard code of 13. What if we changed it to allow 3 dice? Well, 3 dice add up to 18, so we'd have to, change that value there. But anyways, so instead of doing for I in range max score, we could have done it up to the length. For I in range subscript, len subscript, tests, except I said subscript and they were all parentheses. For I in range parentheses, len parentheses, tests, in parentheses, colon. And then print I comma tests subscript I again. That works. Same way, We didn't have to keep using the max score when we could do that. Don't have to use a constant if we can just ask the array for its size. On the other hand, it's not a bad idea. Put your constants up at the top. We know how many test scores we're going to be tracking. Might make it kind of easy to follow. So, that's known as avoiding a magic number. What is a magic number? Why did I pick 4 here? I have no idea, right? But if I made a constant, you know, like number of exams equals 4, and then I did 0 times num exams, that would make sense, right? We would know. Or down here, why did I use 13? Because that's 1 past the maximum roll that we could get with 2 dice. It's stuff like that. So a magic number is just one that kind of appears out of nowhere with no real explanation and should probably be defined as a constant instead. So rather than just use 20 all over your code, define a constant named num underscore or max underscore or something like that. Define a constant, you know, num underscore students equals 20, something like that. Constants are created automatically in many languages. Well, I suppose. Don't know what that means. Sometimes the values stored in an array should be constants. Well, these don't look like constants, but they are. These are strings. We declare an array of strings so that we might be able to ask for the number of sales in January and the number of sales in February and the number of sales in March and so on. So let's do that, although it's kind of tedious to actually have to do all 12 of them. Let's go with it. Months equals, let's only do 4 months, right? Square brackets, quote, Jan, end quote, comma, quote, Feb, end quote, comma, quote, March, MAR, end quote, comma, APR for April. And then let's declare another array called sales, and we're going to put some numbers in there representing the number of sales for January, February, March, and April. Sales equals square brace. In January we had $900 of sales. In February we had $750. In March we had a banner month, $2,000 in sales. And in April we had winter storm, nobody came to our store, and so we only had $200 of sales. All right. Now let's print out the names of the months and the associated sales. Notice that these are linked by their index numbers, right? Subscript 0 for months is January, subscript 0 for sales is 900. February had 750. Element 2 in that list is March, and then we had element 2 equal to 2,000 here. So in March we had 2,000 sales. The last element in that array represents April. The last element in our sales represents 200. So we had $200 worth of sales in April. So let's find out. Let's declare a constant called num months and equal that to the length of the months array. Now we could just say 12, right? but we don't really know that it's 12. We kind of shortchanged ourselves and only gave ourselves 4, so we could hard code it to 4. But why don't we instead ask the months list, the months array, for how long it is? And we can use that in our for loop to print this stuff out. So for I in range, num underscore months, in parentheses colon, print months subscript I, in subscript comma, sales subscript I, in subscript. And we'll see our little sales chart. Right, January 700, February, right, March 2000, and so on. This is what's known as a parallel array. Parallel arrays are when you have 2 or more arrays of the same length, where the elements are linked thematically by their index number, by their subscript. Right, so we have 4 months, we have 4 sales. If we went ahead and added all the months to December, we'd have 12 months, so we better have 12 matching sales. So parallel arrays are when you have 2 or more arrays of the same length, where the elements are linked thematically by the index numbers, by the subscripts. First month is January, the first amount of sales was 900. Second month was February, second amount of sales was 750. So months and sales are parallel arrays. Parallel arrays are 2 or more arrays of the same length, where the elements are conceptually linked, get all fancy, are linked by their subscript. Hope that makes sense. We may not use these, but, you know, F names for first names. And let's make a list of first names. We have Joe, in quote, comma. We have Sue, in quote, comma. And we have Tim, 3 first names. Now let's declare an array of last names. This is an L, not a 1. L names is equal to Joe's last name is Roberts, comma. Sue's last name is Williams, in quote, comma. Tim's last name is Johnson. Needed quotes around it. Quote, Johnson, in quote, end square bracket. And their ages. Joe is 19 years old, Sue is 24, and Tim is 22. And we could have a for loop that prints those guys out. Again, these are parallel arrays. For I in range, parentheses len, parentheses f name, close parentheses, colon. Since these are parallel arrays, we should have 3 elements of each size. So it's okay just to pick one of these arrays arbitrarily, pick one at random, and use that as our length. Because the length of f names is going to be 3, the length of ages is going to be 3. So let's print that out. Print, parentheses, f names, comma, f names subscript I in subscript, comma, L names, subscript I in subscript, comma, quote, is, end quote, comma, ages subscript I in subscript, comma, quote, years old, end quote, in subscript. All right, I made a mistake because I said in subscript. I should have been in parentheses. So you're going to want to fix that if you typed in what I said and what I specified there. All right, Joe Roberts is 19, Sue Williams is 24, Tim Johnson is 22. Another example of parallel arrays. The above three are another example of parallel arrays. And again, the data is thematically linked by the index number. Joe Roberts, who is 19, his subscript is 0. Sue Williams, who is 24, his subscript is 1. And Tim Johnson, who is 22, his subscript is 2. So searching an array for an exact match. This is almost going beyond what I would want to hit today. But I guess we could do this. What if we wanted to find out if anybody in our data here was equal to the age of 24? Well, we're going to do what's something called a linear search. It's called linear because we're just going to do it in a line. We're going to start at the beginning, we're going to go to the end, and if we ever find somebody who matches that age, then we're going to print their name out. So let's look for someone who is 24 years old. So here's what we're seeking for. We're seeking the value for 24. Seek is equal to 24. That's our age of interest. And now we need another for loop. You'll notice that we use for loops an awful lot when processing arrays. They're kind of built hand in hand for each other. For I in range, parentheses, len, subscript, not subscript, parentheses, ages, end parentheses, colon. We need to check that value to see if it's equal to our seek value or our search value. Maybe I'll change the name of that variable to search. So if ages subscript I is equal to 24, colon, 2 equal signs, I would have failed that test question. If ages subscript I equals 24, colon, we found that person. Who is, but not 24 years old. That's hard-coded. That's a magic number. I'm going to change that word to search. If ages subscript I equals search colon, we have the person of the matching age whose age matches. So let's print them out. Print F names subscript I, comma L names subscript I, comma is of the desired age. End quote in parentheses. Maybe I'll add a couple of comments now. That's an end if there. Why am I taking the time? Because now we have nested loops, nested if statements. It's easier to follow if they have comments. Now what if we change that to 25? There's nobody in there named 25, and it's not going to print that anybody was of the necessary age. Right? But Sue Williams was. She was 24. If we had a larger data set, we might wind up with more people of that age, right? If Tim Johnson was also 24, then we'd see it print out 2. There we go, right? Sue Williams is of the desired age, and Tim Johnson is of the desired age. I'm going to change that back, though. 22, or I don't remember what it was before. All right, so we're going to need some homework about this stuff. Create an array called movies. Initialize the array with the names of 5 movies you like. Or if you don't like movies at all, call it books and fill in 5 books. Or if you don't like books, or call the array books or artists or whatever, and fill it in with the data you like. Now we only gave one example. Now we've given several examples, right? Just like that. Movies is equal to Star Wars, Star Wars 2, Star Wars 3, right, you know, that can be kind of repetitive, but you could do that. Then write a for loop, or write a print statement that will print the length of the array, how many elements are in it, using len movies or whatever. Write a loop that will print every movie in the array like this. My favorite movies are, you know, Twilight, you know, Finding Dora, or Finding Nemo, whatever, etc., etc. So that's pretty short, but I think that we're okay there. I think we're okay there. That'll probably take you like 5 minutes. If it takes longer, that's fine. And we got to do one more. We got to do one more. That's part 1. Part 2. Create parallel arrays called colors and foods. Initialize them with values so that you can write a loop that prints the color of each food. For example, I like red grapes. I like green pizza. I like blue cheese. Something like that, right? So, one of the arrays is going to be called colors, and it's going to be set to red, green, and blue. The other one's going to be called foods, and it's going to be set to grapes, pizza, and cheese. Write the loop that would print that out. In the above form. All right. Now we're going to be talking about arrays more, so it's not like this is our only opportunity to understand them. That makes sense? All right.
Can I get a copy?
Yep. I'll print it out. Anybody else want printing to? No other copies? All right.